Okay, so this video is on a topic in the IB Geography course that confuses some people, myself included, before I made this presentation. It's the movement of plate tectonics. Now this can get a bit complicated, as you can see down at the bottom right, with all the layers and how they interact with each other to form our planet. Now the very first thing to know is the layers of the Earth. That is the very first thing you need to learn about plate tectonics. Again, this video is just to refresh people's memories on tectonics just before the geography exam, which is in 5 days for the IB. Good luck to everyone who is taking that. So yeah, the first thing we need to know is just the layers of the Earth and what makes up what. So you have the inner core, which is the very inner part of the Earth. It's circular and it's in the very inside part of the Earth, as you can see the arrow pointing to there. Then you have the mantle, which is then you have the outer core, which is a liquid version of the inner core, which sits just outside it. Then you have the mantle, which is a solid, and it's a thick semi-molten layer that flows slowly. And then the crust is the thin outer layer, which is where we live. Now, don't get me wrong, it's not thin at all. It's quite, with the mantle, the upper mantle, the crust itself is quite thin, but the mantle is quite thick. Okay, so we're going to go into slightly more detail now. The inner core has a diameter of about 2,000 kilometers. Now, this might need to be fact-checked. I saw it was about, online, I think it's about 2,100. So yeah, it's around there. But for the exam, just put 2,000. And it's composed of solid iron and nickel, so it's composed of solid elements. It reaches temperatures of approximately 5,500 degrees Celsius, which makes it hotter than the surface of the sun. So our planet actually contains temperatures hotter than the surface of the sun, which is very, very impressive. The outer core is about 2,100 kilometers thick. Not sure about the diameter, but you don't really need to know that because, again, you just need to know the thickness of it. And it consists of semi-molten metal, so it's like the inner core, but it's liquidized. And its temperatures range from 5,000 to 5,500, so it's slightly cooler than the inner core. Okay. Now, overview of the mantle. Now, the mantle, again, is just above the outer core, and it's about 2,900 kilometers thick, and it's divided into two parts. You have the upper mantle, which contains the rigid layer above the asthenosphere, which we'll get into in a minute, forming a lithnosphere, which again we'll get onto in a minute, with the crust. And the asthenosphere, as I said, we'll get onto it, is a semi-molten plastic-like layer that flows under high pressure, much like warm butter. So it kind of flows underneath the crust, a bit like warm butter. Okay, now in terms of crust, which is where we live, you have oceanic crust, which is of course where the oceans are, and it's thinner and denser and primarily composed of basalt, and yeah, it forms the ocean floors. And then you have the continental crust, which is probably where you're sitting right now, unless you're in the ocean. But yes, so continental crust is what makes up land masses and ecosystems, and it's made up of granite, and it's thicker but less dense than the oceanic crust. Now, this is a bit of a weird concept. I'm not going to try and pronounce that, Mohorovichits, I'm not sure, sorry. Just call it the Moho. The Moho is the boundary between the crust and the mantle, so it's this thin region here. Imagine it's a hidden line that separates our familiar world from the mysterious depths below, marking a significant change in composition and density. Basically, if that line wasn't there, the Earth, like past the crust, it would just go straight into liquefied and really, really hot rocks, where as without that you have it runs under the oceanic crust and it runs under the continental crust. It separates our world from the mysterious depths of the Earth. Okay, now the lithnosphere. This is a complex geological layer formed by the Earth's crust and rigid upper mantle. Now, you can think of it as a giant puzzle that is intricately made up of tectonic plates which float on the semi-molten asthenosphere beneath them. These tectonic plates are in a constant state of movement, gradually reshaping our planet's surface over geological time. This dynamic process plays a crucial role in the formation of mountains, earthquakes, and various geological phenomena. Now, you should know that from the hazards topic, which hopefully I'll get a video on soon, is you get earthquakes when plates move side by side and they slip. You get You get earthquakes. And likewise, you get mountains and fold mountains when they push together, and when they pull apart, you get volcanic activity and earthquakes. But we'll get onto that in a bit more detail in a minute. Okay, so the main forces that actually make the tectonic plates move are convection currents. Now, in the past, the theory of convection currents was used on its own to explain tectonic plate movements, as in the heat from radioactive decay in the core moves upwards into the mantle, creating convection currents, which then makes the plates move. However, more recently, the ridge-push theory theorizes that as new crust is formed, it is pushed up into the spreading mid-ocean ridge, which pushes them further apart. So basically means that as new crust is made, it pushes plates apart. And the slab pull theory, which is the next one, suggests that movement is the result of the weight of the denser oceanic plate subducting and dragging the remainder of the plate along. So, when this one here subducts, it sinks into the mantle here, and it pulls the rest of the plate along with it, which is three theories for why they move. Okay, plate boundaries. Right, now, subduction zones are when they move, when one plate sinks beneath another. Now that one is fairly straightforward. Now rift zones are where plates pull apart. Now there is another name for this, which is divergent zones. So you have convergent, which is subduction. Well, no, subduction zone is when it sinks beneath, but convergent is when plates are heading towards each other. Divergent is when they're pulling away from each other, and transform is when they are side by side, which is what causes earthquakes, for example. Convergent is normally responsible for creating mountains, and divergent is normally responsible for creating volcanic eruptions. So yeah, these boundaries, as I said, shape our landscape, cause earthquakes, volcanic eruptions, mountain formations. A bit like a geological dance. If you just want to take a look at this boundary, this diagram on the right, we have the different plates. So we have the UK and Europe and Sweden all the way up here in this plate here. Then we have most of Africa in one plate, the Middle East in its own plate, then India, and then the Indo-Australian plate, which starts here and runs all the way around here and encompasses all of here. We have Borneo and Southeast Asia, and all of Russia and Europe. It's all on one massive plate. And then most of North America is on this, and a bit of Russia is on this North American plate. The reason that some people get earthquakes in California a lot is because, as you can see, these two plate boundaries are one's going that way and one's going this way, so they're rubbing against each other sideways, and of course California is just over here, and so as these rub along beside each other, they slip and cause earthquakes. Magma plumes and hotspots. Right, so magma plumes are columns of hot rock that rise from deep within the mantle. They create hotspots that lead to volcanic change, such as the Hawaiian Islands, formed as specific plate moves over a stationary plume. So basically, this diagram actually does show it very, very well. It starts here as it rises through the mantle, creates a hotspot. Now, you will get eruptions that then cool, the lava cools, because of course this is magma, and then when it gets to the surface it's called lava. The lava cools and creates volcanoes, which then obviously have, which keep erupting, keep making more volcanoes. So this hotspot stays fairly stationary. And then over here, as the plate moves across it, the hotspot doesn't move. So the hotspot stays still. As the plate moves across it, these volcanoes become extinct as there's no more magma, and new volcanoes are formed due to eruptions and due to the hotspot. And so as the plate moves over the top, these new volcanoes are formed. As I said, that is how the Hawaiian Islands were formed. over many, many years, and they will continue to be formed over many, many years as there is a hot spot beneath beneath the ocean that the plate is moving over. Again, thank you for watching. I hope this video was somewhat useful. Good luck for geography in 5 days, and good luck for the rest of your exams.